have learned the recursion, and recursion we have defined, it is a process of defining an object with itself. We have learned the functions, sequences and sets and structures, how they have recursively defined. Now, today we will read the recursive algorithm, which is a very important and elegant way to solve problems. So, I can define that recursive algorithm is an algorithm that solves a problem by reducing it to an instance of the same problem with smaller inputs. So, we define recursive algorithm. It is an algorithm that solves a problem by reducing it to an instance of the same problem with a smaller inputs. Now, if we remember, we have defined the recursive function, a function. If we remember, recursive function that is a function that invokes itself. Now, very simple way we can tell that recursive algorithm is an algorithm that contains a recursive function. So, since already we know the recursive function and recursive function that invokes itself. So, an algorithm that contains a recursive function, we call that is a, or in this way we can frame a recursive algorithm. So, what is the approach to write or to frame a recursive algorithm? So, approach is, so to frame or how to frame or to design a recursive algorithm. Since just now I mentioned that recursive algorithm contains a recursive function, and since we know how to form a recursive function, then automatically that will the algorithm will call itself. So, we can define in this way that a problem in this class is decomposed into a number of sub problems. It can be one or more than one sub problems of the nature of sub problems are the same as that of the original problem. So, I can write into a number of some sub problems of the same type. Then each sub problem is again decomposed into a number of same sub problems until it gives a or it yields a sub problem that can be solved in a straightforward way. So, the approach is nothing but a divide and conquer method. So, I can tell that recursive algorithm solves the problem in divide and conquer method. So, the approach is the divide and conquer method, that one problem it divides into a sub problem, but nature is same, it is of same type, and again each sub problem another same type of sub problems is, and until we get a sub problem in such that as if it matches with a given condition or it can straightforward way I can get the solution. Then we add all the solutions of the sub problems, then finally the solution of the sub problems are combined to get the solution of the original problems. So, now we describe the method of recursive algorithm design by with a number of simple problems. So, first we see one example, one very simple example of recursive algorithm, that how to compute the factorial of an positive integer. The example is computing or compute the factorial of positive integer. Now, if we remember the recursive function, then how to compute the factorial? All of we know the definition of factorial, that we know the definition that n factorial is n into n minus 1 factorial. Since we know the definition of factorial, that it is n into n minus 1, n minus 2, the product of all integers up to 1. So, this is same as it is up to n minus 1, n minus 2, then it is nothing but the n minus 1 factorial. Now, if we see the nature, that when we are computing the factorial n, that n factorial is n into n minus 1. That means, if I write a function, then as if this function with smaller inputs, because n minus 1 is less than n, with smaller inputs I can frame a function. And recursive algorithm contains this type of function, a recursive function or a algorithm if we write, that contains this recursive function, that will form a recursive algorithm. So, how we use that algorithm? If we write the factorial, we write the factorial or computing factorial of m. So, I can write my input is n, and n is an integer greater than equal to 0, and output is n factorial. Then how I can write? If I give the function name the factorial n then if n equal to 0, then return 1, else return n into factorial n minus 1. So, we see that here this is the function is factorial n, and we have written, when we are computing the function n into factorial n minus 1, which is of same type with smaller inputs, that means n minus 1 is less than n. So, it satisfies the definition of the algorithm, that as if the original problem is decomposed into a sub problem with smaller inputs. So, this is a simple form example of computing factorial n, which is a recursive algorithm. Now, we see another example. Say we compute power. So, we compute a to the power n, where a is a non-zero real number and n is a non-negative integer. Now, we know the a to the power 0 is 1, we know. So, when n equal to 0, it will return 1. So, for n equal to 0, a to the power 0 equal to 1. For other values of n, I can write a to the power n a into a to the power n minus 1. So, as if when we will compute, we want to compute a to the power n, it can be decomposed a into a to the power n minus 1. That means, if I write a function to compute a to the power n, then the similar function with inputs as n minus 1, a n minus 1. That means, since n minus 1 is smaller than n, so with smaller inputs I can frame another function of same type. So, one algorithm that contains a recursive function, and it will be a recursive algorithm. So, very simple way, if I can write, I give the name, that function is compute power. So, it is, I give compute power and my inputs are a n, where a is non-zero real numbers and n is non-negative integer. Now, I can write that if n equal to 0, then compute power or I can write return n, I can write compute power n equal to 1, else compute power n equal to a into compute power a n minus 1, that is a function with smaller inputs I can write. So, this is a recursive algorithm. Now, how we can prove that it is giving a correct result? That means, proving recursive algorithm correct. Now, if we remember that when we have read the recursive function, the way we have proved that the recursive function gives the correct result, and it is using the mathematical induction. Now, if we see that the two simple examples, that if n equal to 0 return 1. So, as if this is my terminating condition, that means there is some condition that where the algorithm will stop, otherwise it is return n into factorial n minus 1. So, I can think that this is my basis step, n equal to 0 then return 1, that means for n equal to 0 it gives some value, and otherwise that I am writing a recursive step which actually contains my recursive function. If I see the next example, again it is same, that if n equal to 0 it return 1, because all of we know that a to the power 0 equal to 1. So, this is equivalent to my basis step, because for n equal to 0 it is giving 1, and then computing power, that is a recursive step, and again this step contains the function and it is a recursive function, because it is compute power n and then it is decomposed into a function which where the inputs are a n minus 1 and my n minus 1 is smaller than n. So, the same way we have proved the recursive function gives correct result, the same way we can tell that we can prove the recursive algorithm correct. So, here also there is some basis step, just now what we have seen, here also there is some basis step which is actually for some primitive values of inputs or primitive values of input results the output, and in respect of recursive algorithm we can tell this is nothing but my terminating condition. That means, when the function can be computed straightforward way. when we stop. So, this is my terminating condition. Then what is my inductive step or recursive step? So, this is my recursive step or inductive step. It is that the algorithmic step that contains the recursive function. So, for the previous example of computing power, I can tell my basis step that for n equal to 0, okay. So, I can write for compute power n, my basis step is basis step is n equal to 0, a to the power 0 equal to 1, and what we have written that if n equal to 0, then return 1 or compute power a0 equal to 1, or I can write if n equal to 0, return 1. So, this is my return 1. This is my terminating condition. And what is my recursive step? My recursive step is that compute power a n is a into compute power a n minus 1. Now, if I use mathematical induction, so if we assume for I equal to n, the result is true. That means, here result is true, that means that is the recursive step gives the correct result, That means, my compute power a n gives a to the power n. This is my correct result. So, for I equal to n plus 1, using mathematical induction, this compute power a n plus 1 is a into compute power according to that algorithm, this becomes a n. Now, for using my mathematical induction, this is equal to a to the power n, since the result is true, we have assumed. So, this becomes a into a to the power n, and this becomes a to the power n plus 1. So, for compute power a n plus 1, this is also a to the power n plus 1, and this is result is correct. So, here also we see that recursive algorithm also we can prove using mathematical induction. This is very obvious because the way we have defined the recursive algorithm, that algorithm contains a recursive function, and the recursive function proving we have used that mathematical induction. So, we can prove in this way the same thing. Now, another very popular example or of computing greatest common divisor, the GCD, using we can write recursive algorithm, that I gave my third example as the computing or compute greatest common divisor, normally we call GCD, of two integers a and b and a less than b. Now, we can write the compute GCD function as the compute GCD in AB. Just if we write that is if A equal to 0, then compute GCD AB equal to B, else the recursive step compute GCD AB equal to compute GCD B modulo A and A. So, this is nothing but our using the computing GCD using Euclidean algorithm. So, computing GCD using Euclidean algorithm. See, if I take an example of, say I want to compute GCD 5 and 8. Okay. Here 5 less than 8. So, I can write GCD 5 8, I can write GCD 8 modulo 5 5, this becomes GCD 3 5, GCD 3 5, then according to the algorithm this becomes GCD of 5 modulo 3 and 3, this is GCD of 2 3, then this becomes GCD of 3 modulo 2 and 2. If I continue, then 3 modulo 2 is, this becomes GCD 1 2 is GCD 2 modulo 1 1. So, this becomes GCD 0 1, and now GCD AB A equal to 0. So, this is equal to B. So, this is 1. So, this is our Euclidean algorithm and we can get. Now, see here the way we have written, this is that compute GCD AB and this is compute GCD B mod A. So, actually this is with my smaller inputs, this is my, every time we are getting that recursive function with smaller inputs. This is my recursive function with smaller inputs. So, we can compute GCD or recursively. So, this is one recursive algorithm for computing GCD, and with this example we see that it is nothing but the implementation of Euclidean algorithm, and in this way we can frame the some simple examples I have given, that how we can design, how we can develop some recursive algorithm which actually there is some basis step in algorithm form, we can write that is my terminating condition, and the recursive step that is my which contains the recursive function, that means the same function with smaller inputs. Now, we will continue with some bigger examples, that how to frame or how to design the recursive algorithms in my next class.